To outfit a single astronaut for a spacewalk, NASA spends roughly $12 million on their Extravehicular Mobility Unit, or EMU. NASA constructs the EMU to serve as a pressurized, articulated habitat, requiring every inch of its surface to serve a specific mechanical function. The human body is built for Earth. Once you step outside an orbital station, you enter an environment with zero atmospheric pressure, zero oxygen, severe ionizing radiation, and high-velocity micrometeorites. To survive out there, the EMU operates as a fully independent anthropomorphic spacecraft. It is an actively running machine designed to artificially generate a complete human biosphere. If we reverse engineer the suit piece by piece, we can see exactly how the physics of a vacuum drives the engineering requirements and the costs into the tens of millions. Understanding that price tag means ignoring the iconic white outer shell and looking closely at the dense mechanical systems hidden underneath. The most immediate threat in orbit is the lack of atmospheric pressure. Without it, dissolved gases in the human bloodstream would expand, causing fatal decompression in seconds. An airtight pressure bladder wraps the astronaut, regulating a personal atmosphere at 1/3 Earth's pressure. But in a vacuum, internal pressure pushes outward, making the bladder rigid and locking the joints. To solve this, machined bearings are inserted to allow the limbs to articulate. This structural complexity extends to the hands. The gloves are heavily engineered assemblies that must maintain a critical pressure seal while still allowing enough finger dexterity to operate intricate hand tools. Because the astronaut is constantly fighting the outward force of the pressure bladder, simply bending an arm or gripping a handrail requires immense physical exertion. A spacewalk is a high-fatigue mechanical challenge. The second major environmental hazard is thermal variance. Temperatures in orbit swing from 120 degrees Celsius in direct sunlight down to negative 150 degrees in the Earth's shadow. The suit's heavy exterior insulation protects against these extremes, but it creates an internal consequence. The astronaut's own metabolic heat is completely trapped inside the sealed vessel. Inside a closed, pressurized bladder, sweating is entirely useless for dissipating heat. To manage this, the astronaut wears an active thermodynamic system called the Liquid Cooling and Ventilation Garment, or LCVG. Here we see how the LCVG functions. It circulates cold water through a dense net of heat and transports it outward. Without this active thermodynamic loop constantly running, an astronaut would suffer fatal hyperthermia within minutes, entirely independent of the freezing temperatures outside the suit. The massive backpack serves as the primary life support system, the mechanical core that actively regulates the astronaut's internal atmosphere. Stripping away the outer casing reveals a tightly packed array of active mechanical processing units and plumbing. Its primary respiratory function is twofold. It steadily pumps pure oxygen into the helmet for the astronaut to breathe, while actively scrubbing out the toxic exhaled carbon dioxide. It also handles secondary tasks, extracting dangerous humidity, filtering out trace gases, and distributing necessary electrical power. The margin of error here is zero. If this closed-loop processing stops, the astronaut will lose consciousness in seconds. The PLSS is the mechanical pump that physically sustains the artificial biosphere. Engineering a system this dense and reliable accounts for a massive portion of the suit's total engineering footprint and cost. Moving outward, the suit is shielded by more than 10 stacked layers of material. These strata act as armor, absorbing high-velocity micrometeoroid impacts and blocking incoming solar radiation. The helmet locks securely into this outer shell. It houses continuous audio communication systems and features a specialized visor to filter out undiffused solar rays. Everything built into this suit must account for the supreme engineering constraint of orbital operations. During a spacewalk, there is absolutely zero time or capability to execute on-site repairs. This dictates a mandatory engineering philosophy, fail-safe redundancy. Every critical survival mechanism must have an immediate backup. This flowchart illustrates that principle in action. The oxygen, electrical power, and thermal cooling systems all utilize dual parallel architectures. If the primary circuit fails, the dormant secondary circuit instantly takes over. Requiring every single essential survival system to exist twice within the same compact footprint exponentially multiplies the fabrication complexity of the unit. Which brings us back to our opening premise. Why does outfitting one person cost $12 million? The price tag is a direct mathematical function of the sheer density of custom fabricated survival machinery compressed into a human silhouette. Every single valve, rotating bearing, and cooling tube is machined to exact specifications and put through extreme testing tolerances, because a single micropuncture is a fatal event. You cannot rely on mass production when zero-margin failure constraints dictate the entire engineering pipeline. Out in the vacuum of space, human survival is never left to luck. It is purely dictated by the reliability of these active closed-loop systems. The Extravehicular Mobility Unit represents humanity's most sophisticated portable machine, utilizing active mechanical systems to sustain life in a total vacuum.